Okay, so in this example, I'm given this vector equation, and I want to figure out if there's one solution, infinitely many solutions, or no solutions. And if there's finitely many solutions, we want to express the solution as a set. If there's infinitely many, we'll pause and we'll deal with that in a later section. So looking at this vector equation, what I want to do first is set up an augmented matrix that represents the vector equation, or equivalently, the system of linear equations. Once I have the augmented matrix, then I can row reduce it and interpret that to come up with a simpler system of equations, and then that will tell me how many solutions I have. So first, let's create our augmented matrix. So I'll have a column for each variable, and it turns out that the columns will be exactly these vectors here, because this first vector are all the numbers that are being multiplied by x1. So I have -2, 1, -3, -8, and then -6, 3, -9, and -24. And then finally -1, 4, -4, -1. Then my vertical line to say that this is equal to my constants. So 4, 5, 1, and 22. Remember, the way that we read this augmented matrix is -2x1 minus 6x2 minus x3 equals 4. And that's exactly what the first row of our vector equation would tell us, right? If we think about expanding or distributing the x1, x2, x3, combining into one vector, right, we'd get -2x1, -6x2, minus x3 equals 4. So I've transformed this vector equation into an augmented matrix. Now, what I want to do is row reduce this, and I'm going to use my calculator. Okay, but it's important to see what the original matrix is and what the new matrix is in the reduced row echelon form. So I'll just say we're using the reduced row echelon form. Okay, now that we're past LE2, we don't need to worry about showing our work for this. We're able to use our calculator. But I want to see the starting point and the ending point. So what matrix do we get? Well, going across from left to right, I get 1, 3, 0. Then my vertical line, -3. And then 0, 0, 1, 2. And then the last two rows are all zeros. Okay, so again, totally fine to use the calculator, but I want to see what is our starting augmented matrix and then what is our resulting augmented matrix. And now I can go back into a system of equations by reading across each row. So x1 plus 3x2 equals -3. Okay, then in the second row, 0, 0, 1x3, so x3 equals 2. Then 0x1 plus 0x2 plus 0x3, that's just 0, equals 0. And then 0 equals 0. Okay, from here, we can use this information to figure out how many solutions we have. So the first thing I notice is I don't have any contradictions. I don't have any equations that are always false, right? 0 equals 0, 0 equals 0. They don't really give me much information, but at least they're not false. So that's fine. We have true information. So that means we at least have one solution because there's no contradictions. Remember, contradictions are what tell us that we have no solution. So we either have one solution or infinitely many. And we would have one solution if our equations said x1 equals this, x2 equals this, x3 equals this. Now we do know what x3 is equal to, but there's no equations that say x1 is equal to this number, x2 is equal to this number, and so that tells me, since the variables are not isolated, I don't have a value for each of them, that tells me we will have infinitely many solutions. Okay, and for now, that's the best we can do. We will worry in a later section about how do we express the solution set when there are infinitely many solutions. But for now, our instruction said just write the solution set if there are finitely many solutions. And so for now, this is done. We took our vector equation, put it into an augmented matrix, row reduced went back into the system of equations and interpreted this new system of equations to say, hey, it has infinitely many solutions, and since the row operations preserve the solutions of our linear equations, then this vector equation will also have infinitely many solutions.